So the system we're using is a form of a Highline system. This one in particular is an English Reeve, and we're using a dual Trackline English Reeve. And what that allows us to do is run a lifting and lowering line, or what we call a Reeve line, at any point along the track lines, and that allows us to lift and lower and then move the trolley back to our working station for processing. Going over some of the components, we've got an anchor point on either side of the Highline span. For the most part there, we're utilising our custom-made frame that attaches to the front of our skid steer. That allows us to have high redirect at points where there isn't any trees. And then on the other side of the Highline, we would use existing trees for that. For the trees and for the skid steer attachment, they'll be braced back using guy ropes and straps so that the vector forces of our Highline are not wanting to pull over the trees or the frame. We use large slings and, where needed, some protective matting in the trees. Our slings, for the most part, are utilising like a 2-ton round sling, and that provides us with adequate safe workload even in a choke configuration. Our two track lines seen here, we have our top track line is a blue line that runs down to here and is terminated over here, and we have the red track line that runs through here and is also terminated down the frame. Those both Donaghy's 12mm super speed with quite a high braking strength. Our system utilises a 5-to-1 safety factor, which leaves us with a working load limit of our track lines of about 15 kilonewtons each, so around about 1,500 kilos for each of the track lines. They being the limiting factor in the system, as we would reach the working load limit for the track lines before we reach the working load limit of any of the other components in the system. We're moving down through the components here. We've then got the Reeve line, or in this configuration here, this is the setup for the longer spans, and that we have two separate ropes joined over here with a swivel. This yellow Reeve line is what allows us to lift and lower the loads. That then runs along and is controlled via the GRCS, the capstan winch. We use battery-powered drill to raise the loads up. There's some limiting factors or some things to be aware of when we're setting up this join in the rope here. We've used this to allow for a much lighter rope to run for the majority of the span. So that utilises 10 mils Donaghy super speed, and then we join in 16 mil or 14 mil. Yeah, we join in a 14 mil rope into joined in there by the swivel, and that's what's actually directly driven into the GRCS so that it self-tails. The limit with that is that we just have to, when we set that up, we need to have the hook and the block raised all the way up to the trolley here, and we need to have this join in the ropes all the way back to the frame anchor, or what we would refer to in our systems as the near side anchor, as opposed to the far side over here. So that needs to be brought over here, and this one raised up before we tie off the tail of the rope over on this end. That way it allows us to get the maximum distance that we can lower the hook before this join in our rope meets the side of the trolley here. And that allows us, for the most part there, provided that this distance between where our frame is, and where we need to pick up things is at least twice the length or distance between the bottom side of the trolley and where we're picking the loads. Moving down to the green line, or the green lines, again, this is shown for the setup for longer spans. So the components here setup is designed for about 100 meter spans. This extra green rope here and this setup here allows us to increase the speed at which we pull the material back along up the track lines for quicker turnaround time. So the components we have here are a 12mm double braid rope, runs back to our redirect on our frame, comes down and goes through a redirect at the base of the frame on the working platform, and then into the capstan of the EDA 1800 petrol powered winch that we use. It's a 2-stroke powered winch. That allows us to haul that up the line. And in the second gear, that provides with a straight pull, we get a 900 kilo force at 24 meters a minute. But with this reverse mechanical advantage system, by running that up through along here and back to the trolley, we can increase that to approximately 48 meters a minute, but that does reduce our strength, our pull force, but that is plenty sufficient for as we're guiding the pieces up along a track line. So the forces on that it actually needs to pull up the incline of the rope is quite minimal. The additional petrol tandem speed trolley along here, additional to the DMM Keanu that we use over here, is just to keep these components, the swivel and the pinto pulley here, from sagging down and getting caught in other branches. So that just runs along on the track line there. And moving on, having a look at the Keanu trolley itself, we've got the top track line that goes into an additional Edelrid pike pulley. Then the second track line runs through the pulley sheaths of the Keanu, and then the Reeve line also runs through the pulley sheaths of the Keanu. We install a couple of eye bolts through the attachment holes just to pass the side, one side of this reverse mechanical advantage rope along through there so that it doesn't sag down and get caught up in any of the other parts of the system, the hook or foul in the line here. All of the ropes utilize swivels in line. Any of the ropes that will interact with lowering bollard or a capstan have swivels in line. So depending on the setup, if the far side anchor is higher than where our skid steer frame is, a near side anchor, then sometimes we will use friction device like a quarter wrap on the end of this to control the descent of it. But for the most part, we're on raised ground above the gully and where our near side anchor is, so we're pulling that up the incline of the track lines. We keep a swivel in here in case that is needed there. This line here is part of the reverse mechanical advantage. That doesn't require a swivel. It is not really. It is just getting run through the pulley here. 2 track lines have swivels built into their attachment point hooks. That is as we tension up the track lines, we introduce some twists into there, and that's just to be able to let them out of the system. The Reeve line employs the swivel in the join between the two, and that allows for the twists to be let out of the system. There's lots of twists introduced when we use the GRCS. There's an additional pole on this side of the frame that's not shown here just for clarity of the rest of the components, but that's where the GRCS mounts. When we have a look further back over to the frame here, we have a tensioning system that is projected onto the 2 track lines. So initially, depending on the span length, each track line will just be hand tensioned by a few people and then tied off onto the bollards on either side. Then double prusik will be utilised on each of those track lines and then running down into a tensioning system that equalises out the tension that's applied on each of these track lines. That's usually done via redirecting the tail of the tensioning line onto a GRCS, and we can monitor the tension that we apply on that through our line scale, which sits in here. The line scale load cell that sits in here. The Prussic here is just for progress capture of that tensioning, so that once of the tensioning line, once we have applied the pre-tension that we want to the lines, then we then take the tail of the tensioning line and we wrap that around a bollard down here, and then we remove the Prussic from the system, and then these lines here are now forming part of the overall trackline systems, and these parts here are left tied off but with slack in the system. That's a part that we just need to monitor in case we have a high load on the system and they slip. They will still be held by here, but we won't get a true reading from our load cell here, so that we just monitor that they maintain slack. In terms of the trackline tensioning system and the load cell, the line scale 3 load cell that we use, that gives us a readout at the bottom in here that shows the load that's applied to each of the track lines. So with our track lines having a workload limit of 15 kilonewtons, that will show us the live reading as we lift pieces or pre-tension pieces. Then the load cell here will give us a reading on there. There's a few things that we need to look out for when we're setting this up, and that is we need to keep the spacing between the lower track line and reeve line, the reverse mechanical advantage termination of the whole line, and the redirect for the holdback or return line. They need to be kept spaced fairly well apart, a good metre or so apart, just so as any slack in the system as it's generated there isn't, we can get bindings of these ropes around each other. It's also really important when we're pulling in we're hauling the line on the EDO winch, or as we're lifting the loads in the GRCS, that we have the slack out of the system first before we start winching, as any slack in the systems can cause the wraps on the capstan of either the EDO winch or the GRCS to jump over each other and bind up. Some of the trees that we use this for, depending on where we are in the diameter of the tree and the integrity of the rest of it there, we utilise, and our intended travel of the path. If we're deviating to the sides at all, then we'll want to install multiple guy ropes bracing the tree back, and likewise with the frame on this end. And it is a reasonably complicated system, or a reasonably complex system, but once it's understood, installed, it can provide a very efficient turnaround time. Depending on the length of the span, it's quite easy to get fixed out in less than a couple of minutes and returned back again. The system requires about 4 people, depending on it requires a minimum of 4 people to operate. Yeah, it's really useful for areas where there isn't access for a crane to get in and or other machinery. It requires really clear communication between the crew members. We utilise two-way radios for the longer distances and Bluetooth intercoms between the crew members that are working close by.